Okay, this is a review for test number 2. So I'm going to discuss the first problem. Calculate the double integral of this function. Okay, the domain is going from 0 to 1. This is a square actually. So the domain is a rectangle, so it's easy to use Forbidden theorem. Okay, it doesn't matter which one you want to use first. But when you look at this, I find out I prefer to use the y variable inside and the x variable outside. Okay, so the entire derivative of this function will be natural log of 1 plus xy. Okay, so when you differentiate with respect to y, you get x over 1 plus xy. So now you're going to get natural log of when you plug y for x, okay, and plug 0 for y, you will get 1, natural log 1, which is 0, so dx. Now the problem is how to evaluate this integral. Okay. Well, we have to use the integration by parts to evaluate. Let's find the entire derivative of this function. So you begin with the indefinite integral by the chain rule, by the integration by parts, which is going to be x natural log of 1 plus x, then integral, okay, and the x times the derivative of natural log. Okay, got it? The derivative of natural log of 1 plus x will be just 1 over 1 plus x. All right, so this is it's a u and a v. So this is like the u and dv, okay, which is going to be uv minus v du. Okay, v is x here, u is natural log 1 plus x. All right, but how do you evaluate the integral of x over 1 plus x? Well, the quick way to do is going to be express x as x plus 1 minus 1. Okay, then you will get 1 plus x here. Integral, this will be 1 over, right? It's integral of 1 minus, I don't need to use a parenthesis. All right, so the first term will be x. The second term will be natural log 1 plus x. Okay, and plus constant. Now you can double check when you differentiate whether you get natural log of 1 plus x. Okay, you can check that, right? So check. Don't worry about that. So the derivative of x natural log of 1 plus x and minus x plus natural log of 1 plus x is going to be natural log of 1 plus x. So the derivative of x will be natural log of 1. Natural log of 1 plus x, yes, minus 1 plus, okay. So yeah, after simplifying, you can quickly see that it's 1 plus x. We're done. So we find the antiderivative of that function. So how to evaluate this integral? You just take the difference of the end to end point. Okay, when x plus when 1, yeah, plug 1 for x, you get natural log of 2 minus 1 plus natural log of 2. Okay, this is the first part. Minus plug 0 for x. I think it's going to be 0 minus 0 plus 0. So anyway, it is going to be 2 natural log 2 minus 1. Okay, so this is the answer. So this is double integral. You can, yeah, you have to use substitution or integration parts to evaluate this integral. The next question is set up iterative integrals for both orders and evaluate the double integral using one of the orders. Okay. Set up iterative integrals for this double integral. Okay. And then where d is going to be bounded by y equals x, y equals 4, and x equals 0. Okay. All right, so set up iterative integrals for this, right? And evaluate. Okay, then evaluate one of them. All right, so now what I'm going to do, very first step, you have to draw the region, right? So this is going to be the strict line y equals x, y equals 4, and x equals 0. So this is the region. Okay, make sure you draw the correct one. Okay, so this is a 4. It's a 0. So the intersection here is 4 and 4. So okay, you can use a horizontal line segment to set up iterative integral. If you use a horizontal lines, so that means you take an arbitrary y between 0 and 4. So 0 and 4, dy put outside. Okay, then x is going to be run from 0 to some point here. So what is the upper bound for the x? Well, it's determined by its x is equal y. So it's 0 to y, because this should be dependent on y, right? So y squared ex, right? And then dx. Okay. You can also use, you can also switch the order, right? So use a vertical line to evaluate integral. Okay, so you pick up x from 0 to 4, and for each x, you have to determine the upper bound for the y value and the lower bound for the y. The upper bound for y value is 4. The lower bound for the y value depends on x, just x. Okay, because this line is y equals x. So it's x, y squared e to the xy, and dy. Which integral is simpler? I think the second one is a little bit more complicated because it's a function, you know, it's integral with respect to y variable. Integral with y variable, right now, you have y squared, right? E times e to the x times y. X is real as constant. So I don't think it's easy to evaluate. So I'm going to use the first one instead of the second one. The first one, just evaluate with respect to x. So the antiderivative of y squared times e to the xy, dy is a constant, then the antiderivative will be y, e to the x times y. Okay? Because when you differentiate with respect to x, you get a y. So get y times y is y squared. So from 0 to y and dy. Okay? So when x equals y, so you get a y squared. When x equals 0, you get the y times e to 0, so just 1. So what is the antiderivative of that function? Well, you can use substitution, but there's a quick way to do, right? So the antiderivative y e to the y squared will be, when you differentiate, you get 2y times e to the y squared. So you have to divide by 2 because you just get a y here. and here's half of y squared. So this will be the antiderivative. Okay. And then you can, of course, you can use substitution step by step. I just want to show you how to write. I can write down the antiderivative directly because I guess it's what e to the y squared. But when I differentiate, I get 2y, so I have to divide it by 2. You want to just get a 1. Okay, so now you get half of e to the 4 squared minus half of 2 squared. Then I plug 0 for y. I get 1/2 e to the 0 minus 0. Okay, so the answer will be half of e to the 16 minus 8 minus 1/2. Then, right. So this is so this example shows you have to find a bet. You have to carefully choose one of the iterative integrals so you can quickly evaluate the integral. Okay, if you switch the order, it will be much harder. The third problem I want to discuss is to sketch the region of integration and change the order of integration. Okay, so you are given an iterative integral. You cannot evaluate. The reason is the function is not given specifically. So sometimes I give you a very specific function, but if I'm not asking you to evaluate the integral, don't do that. Okay, it's a waste of time. So read the question carefully. Okay. So very first step, you have to determine the domain. And then you can figure out whether we can use horizontal lines or vertical lines to partition the domain, the region. Okay. So then you can switch, you know, if we use the vertical lines, then this time you can use horizontal lines. So how do you understand that? So y is outside, right? Y, okay. So y is between -2 and the positive. Then for each y, what is the range for the x variable? It's clearly between 0 and 4 minus y squared. Okay. So okay, let's look at the case when x equals square root of 4 minus y squared. This is equivalent to x squared plus y squared equals 4, but x is greater than 0. So that means it's epicenter. Okay. Epicenter circle. Okay, circle. So what's the radius 2? -2 and the positive. Okay. So this is as a subcircle. All right. So what I'm doing here, is, okay, wait a minute. X is between, sorry. So X is greater than, no, the right semicircle. It's my mistake. Right semicircle, okay? Because X is greater than or equal to 0, x squared plus y squared equals 4. So this x greater than 0 is on the right hand side. Okay. So what I'm doing here is for x fixed y, I look at the horizontal line. So x is between 0 and the x value of that point. The x value of that point is determined by square root of 4 minus y squared. Okay. So here x is going to be square root of 4 minus y squared. Okay, anyways, this is going, if this domain is called D, so this integral is double integral of the function. Okay. Now if you use vertical lines, okay, if you use vertical lines, x is between 0 and 2, clearly, right? X is between 0 and 2. Okay, for each x, right? This is for each x, you have to determine the y value, the range of y value for the vertical line. So here's f of x, dy. So clearly, y is, well, if we solve it for each x, y is going to be plus or minus a square of 4 minus x squared. Okay. So the lower bound will be negative, the upper bound will be positive. Okay. So this is what I want you get. So you have to draw the region first before you, then write down the double integral and express clearly what is d. Okay, the domain is important. This is a part of the solution. Okay, I'm not very interested in the final answer. I want to see the procedure, how to get it, right? If you don't show to me, my question is, did you copy from somebody else? Okay, so this is a problem number 3. So problem number 4, okay, evaluate the integral by changing polar coordinate, by changing to the polar coordinate. Okay. Right, so this is double integral d, x squared plus y squared minus 1 dA. What is d? Well, d is going to be bounded by the semicircle and the y-axis. Actually, this is the same d as above. Okay, so let's look at the picture. Okay, it's negative 2 to positive 2. This is a d. The best way to evaluate this double integral is use a polar coordinate because the region is very nice. It's just a portion of the circle. So if you use x equals r cosine theta, y equals r sine theta, what you should put on the what kind of restriction you have to put on r? R is between 0 and 2. How about theta? I think theta, this is the angle theta. So theta is between negative pi over 2 and the positive pi over 2. Okay, clear, right? So you get the whole semicircle. So, and now if you use this substitution, the double integral, this is a domain for d bar, right? Okay, so this is a domain in the polar coordinate system. Okay, so this double integral is going to be this double integral on the r theta domain plane. Okay, so here x squared plus y squared is just y r squared. Then you have another r here, then dA bar. So things d bar is going to be the rectangle. So I can choose any of them. Okay. I can choose any of this order. Okay. I can put a d outside. So I is from 0 to 2. Then d theta is between negative pi over 2 and the positive pi over 2. And here r squared minus r and d. Right? Now, since the function is independent of theta, so you get just take out and the difference between pi over 2 and negative pi over 2. Okay, so it's just equal to pi. And then the antiderivative, so it's going to be r squared minus 1 times r squared, so r cubed minus r dr. Okay. All right, then you find the antiderivative. So you get pi quarter 2 squared to the 4th power minus 1/2 2 squared. Okay? So you can simplify a little bit. So 2 to the 4th is 16. It's actually 4 minus 2, right? That's 2 pi. So the answer is 2 pi. Number 5. Okay. Okay. We're going to find the mass and the center of mass. Okay. Of the lamina that we have to draw the picture, okay? That occupies the region D, and the density function is also given. Rho equals R squared. Okay, what is D? D is bounded by y equals x plus 2, y equals x squared. Okay, so you have to draw the D first. All right, let's draw the D. So y equals x, that's 2. Y equals x plus 2. Y equals x squared. Okay, so you get 2 points, and this is a D. Okay, there's no symmetry here. So clearly the center should be somewhere here. X bar and the Y, right? The center of mass. So write down 2 formulas before you do a calculation. Okay, so intersection, first we'll find the intersection part, intersection points. So x squared equals x plus 2, x squared minus x. Okay, that'll be x minus 2, x plus 1 equals 0. So x equals -1, y equals 2. X equals 2. So when x equals -1, y is 1. When x equals 2, y is 4. So 2 and 4, and the -1 and 1. Y is 4 because y is x squared. Okay. All right. So first of all, you find the mass, right? That's going to be integral. I think I'm going to use this is double integral. Okay, rho dA. Okay, write down the formula. Okay, and yeah, this is double integral of this. Okay, actually, it's going to be it is going to be the, you can evaluate this later. Okay, let me continue. So x bar is going to be 1 over a, right? A is in there, and this double integral, okay, of x times the density function. Okay, right? And the y bar is going to be in double integral of y rho and dA. Okay. Then you just evaluate these 2 integrals. Let's see. This is in section 11, 15 point. Let's find out where it is. It is application of double integrals. Yeah. Okay. So there are 2 formulas given in the book. Okay. So now the next step is just evaluate this integral. Write down the correct formula. Right. Okay. Now you maybe remember if the density function is constant, then there's other formulas you learned before from math was 65. Okay. All right. So let's find out what is A. This is double integral. Rho is x squared, right? Rho is x squared. So let's look at, let's use a vertical line to evaluate double integral. So from -1 to 2, so dx is all side, and the y is going to be depends on two functions. The lower bound is x squared, the upper bound is x plus 2, okay, dy. So the density function is independent y, so you just needed to take a difference. So x plus 2 minus x squared and dx. Okay. Okay, computation is a little bit complicated. It's going to be, x cubed plus 2x squared minus x to the fourth. All right, let's find out the entire derivative. Okay. You will evaluate the two endpoints. You should get a positive number because the function is positive. It's an integral positive function. Okay. All right. So let's look at this. Okay. 2 to the fourth power, 2 over 3, and the 2 cubed minus 1/5, and the 2 to the 5th. Okay. Well, it's a little bit difficult, right? And I have to put a negative sign here. -1. So you have to simplify this part. Okay. Yeah, let's do some calculation of this. I hope we can do that, right? So clearly I can take 2 to the fourth power out of the first one. So I get quarter plus 1/3, okay, minus 2/5. Yes. Okay, let's quickly do the computation. So 7 over 12 minus, okay, so it's going to be 60 here. 24, okay, 11 over 60, okay? So this is a number, first part, 11 and 2 to the fourth power, and 60, minus, this next part is going to be, okay? So the next one will be -11, 1360. Okay, so it's kind of complicated. 11, 24 plus 13. So this is a very strange number. I'm not sure I should complete this whole computation. So then this is a total math. Okay, and then how do you calculate the x? How do you calculate the y bar, x bar? Right, you have to calculate this double integral. X times rho dA, right? This double integral, because rho is x squared, so x cubed. The rest of them are similar, right? And then again, the integral becomes, right, x cubed dy and then dx. Yeah, we just want to complete the x bar. Okay, so you will get the integral. Yeah, this is x cubed is independent y variable. So x cubed x plus 2 minus x squared dx. So I get x to the fourth power minus 2x cubed minus x to the fifth. Okay, so the antiderivative now is quite different. It's going to be 1 over 5, and that is going to be 2 over 4x to the fourth power. And evaluate at the two endpoints. Okay. First, you will get 2 to the fifth plus 4 here, 2 to the fifth also, and a 2 to the sixth. Okay. Minus negative 1/5 plus 1/2 and minus 1/6. Okay, it's a little bit complicated, right? So let's get to the number, okay? And I can take 2/5, 2 to the fifth out. So get 1 over 5 plus 1 over 4 minus 2 over 6. 2 over 6 is 1 over 3. Okay. So 12, 3 minus 4, negative 1. So 60, 12 minus 5. 12 minus 5 is going to be 7. So 7 times 2 to the fifth over 60. Okay. So let's do the next one. So 1/2 minus 1/5 is going to be 10 here. 5 minus 3. 5 minus 2, so 3 over 10. 3 over 10 minus 1 over 6. It's going to be 60 in the denominator. Okay. Yeah, you will get 16 minus 10, so 8 over 60. Let's use 8 over 60. Okay, I'm not, yeah. So I have to combine them. Okay, so there's a common denominator, right? So x bar is just a ratio of these two numbers. Okay, this will be 7 times 2 to the fifth minus 8 divided by 60. And another one, I should carefully choose a number, yeah. So another one is 2 to the fifth, to the fourth, and plus 13. Okay, 66 cancel out. Yeah, it's kind of a very strange number. So this number is positive, clearly. Okay, it is positive, and so it matches with the picture here. Look at the picture here. This is going to be x bar should be positive. Okay, so I'm not going to work on the next y bar. Okay. So what is next step? Number 6. Find the area of the surface. Okay. Okay, the surface is defined as follows. That is a part of the plane 6x plus 4y plus z equals 6. Lies inside the cylinder. Okay. X squared plus y squared equals 25. So let's draw the picture first. So this is a cylinder. Okay. And how do you draw the plane? The plane is kind of passing through the, okay, here's the way we do. When y, z both are 0, x is going to be 1. So 1 is inside here, okay? When, when x is 0, when x is 0, x is 0, y z is 0, y is going to be 6/4. It's somewhere here. Okay. When x is 0, y equals 0, z is going to be 6. 6 is very tall. Yeah. So it actually the plane is passing through these 3 points. So the intersection part is hard to draw. Okay, it's going to be somehow like that. Okay, this is it's hard to draw. It's anyway, it is inside. It is inside the cylinder. Okay, so what we needed to do is just find write down the integral first, because this surface is going to be the graph of a function over the domain D. Okay, so the surface is the graph of the function f, okay, over the D. So what is f? F can be solved, okay? F can be solved by the following. So z equals 6 minus 4, 6x minus 4y. So that is my f of x, okay? And the D is going to be x and y here. X squared plus y squared should be less than or equal to 25. Okay? So that is the D. So let's get it. So now the area, write down the formula. It's double integral over D, square root of 1 plus fx squared double y squared dA. Okay, you should write down that first. Then you do the computation. Oh, okay, and then you have to find the derivative. It's going to be -6, -4. So the integral, the square root of 1 plus fx squared plus fy squared is going to be constant. So a is going to be double integral and square root of 1 plus 6 squared, right? Plus 4 squared and dA. If this is constant, you can take it out. Okay, 6 squared this is going to be 252. So square 53, double integral. And this is just area of the disk. You don't need to use polar coordinates, for example, to evaluate this double integral. It's constant. Okay, if it's not constant, then you maybe have to use a polar coordinates to evaluate this double integral. Okay, so this just is the area of D, which is pi r squared. R squared is 25. This is a 53. Sorry. Right. So that is answer 7. Evaluate the triple integral e to the z of y dv. What is e? E is determined by the following 3 inequalities. Okay. Be careful. It's harder to draw it. Okay. If you have to draw, you can, unless I want to switch the order of the integrals. Okay. So basically, this is the order. Okay. You have to y is between 0 and 1, and for each y, x is between y and 1. Then for each x and y fixed, z is between 0 and xy. Okay, so it's layer by layer, okay. So the triple integral should be expressed in the form like a dy is all side. Then dx, and here is going to be 0 x times y, and dz. Okay, don't just randomly switch the variables unless you understand the picture. Maybe you can switch it, but you have to use the domain D this region E. Okay, if you're able to draw it, maybe you're able to switch the order. Okay, so how do you draw it? Here's x, this is y, that's z. This is z, this is y. So for each y between 0 and 1, x is going to be between x is going to be between y and 1. Okay, x is 1 is here, and x equals y. Okay, so we are for each y, I get this region. Okay, then for each x and y, I have to look at the z. Z depends on x and y, it's upper bound, right? So x times y along the z-axis is 0, along the y-axis is also 0. When y-axis x is 0. So when x equals 1, y equals 1, it is here. Okay, so the graph looks like that. Okay, so it's like a triangular type of a roof. Okay, but touch like a tent. Okay, and the other two sides touch the ground. Okay, other two sides touch the ground. So I think it's kind of difficult to yeah, it's kind of difficult to draw. You know, this is it's actually cut it from here. It's not an extent. Yeah, it's hard to exchange the order of those variables. Okay. Okay. All right. So let's evaluate step by step. So this is already given. So the derivative with respect to this is the integral with respect to z. So the antiderivative will be y e to the z of y. Okay? When you differentiate with respect to z, you get e to the 0, z over y. Right? So this is a dx dy. Okay? Replace z by xy. All right, so let's simplify a little bit. So it's y e to x. Right, so dx dy. All right, so here y viewed as a constant and x is variable, so the antiderivative of this is y e to the x minus y times x. Okay, when you differentiate with respect to x, you get the function back. Then you replace x by 1, then replace x by y. Okay. So now you have to evaluate this integral. Okay. The only difficult part is the antiderivative y turn e to the y. Okay. And this one, let's do the quick computation. Use the integration by parts. Okay. And this is dv. Okay, v is going to e to the y. So y times e to the y minus, you switch the order. That's u and du, so ey du, dy. So you can check that this will be the antiderivative of the function, y times e to the y. Okay. So the so here e minus 1, right? And times y. So antiderivative, this will be y squared minus, this will be y e to the y minus e to the y plus 1/3 y cubed. Okay. Evaluate the two endpoints. So plug 1 for y, okay, 1. That's going to be 0. Okay, that's the first part. The second part, you plug 0 for y. That's going to be 0. I think y is 0 squared 0, negative 0 times e to the y. 0. Then plus e to the 0, it's 1. Okay. So that is the answer. Is it positive or negative? Okay. If it is, yeah, this should be a positive number, okay? Because e to the 0 of y, this function is positive. Okay, double check, otherwise it's mistakes, right? It's hard to check that. Okay, we can do like this. 3 e minus 3 minus 4. It's minus 7. I think it is going to be, it's 2.7 times 3. 7.4 minus 7. It's a positive, okay? Yeah, when you get answer, double check. It's common sense because the function is positive, so the integral of the function should be positive. I hope that's my computation mistakes. So number 8. This is a triple integral e z dv. E is enclosed by the parabola, paraboid. Okay, z equals x squared plus y squared, and there's a plane z equals 4. All right, so paraboid looks like that, the typical, and x equals 4 is 4. Okay, so we're talking about the e is inside here, so those are the, okay, this is it. Okay, this is e. All right, so how do you do that? So I prefer to, there are many ways to solve the problem. You can use polar coordinate, cylinder coordinates. You can use iterative integrals. Okay. Now let's use the iterative integral. Okay. Essentially, it's a cylinder coordinates. Okay. So this is a projection onto D, right? So the D, okay, x squared plus y squared is going to be 4. So D is going to be x and y, x squared plus y squared less than or equal to 4. Okay. Yeah. Just look at the circle. The intersection with the plane z equals 4. So x squared plus y squared is going to be 4. Okay. So the domain is going to be determined by this inequality. X squared plus y squared less than or equal to 4. Right. So this should be equal to the double integral dA. Then for each point x and y, you draw a vertical line segment. So think about what is the lower bound for the z value. The upper bound is for z is 4, right? The lower bound for the z is actually is determined by the paraboloid. Okay, that's it. So this is a. You can also use a slight different way. You know, you can. There are several ways to set up the iterated integrals. Okay, I will give another iterated integrals, but right now finish this first. So the antiderivative is half of z squared. Evaluate as these two endpoints. All right, this is a double integral on this disk, and here's 4 squared minus half of x squared plus y squared, and dx. Clearly, we have to use a polar coordinate here. Using the polar coordinates, it's a disk, right? So it's a disk. I is from 0 to 2. Theta is from 0 to 2 pi. And here it's going to be 8. Half of x squared plus y squared is r squared. And this must be r here. And d theta dr. Okay? Theta, it's constant, so you take theta out. It's 2 pi dr. Okay? Then you find the antiderivative of this function. 8r minus 1/6r cubed. R cubed. Okay. So evaluate 2 endpoints, just plug 2 for r, then we are done. 8, 2, 1/6, 2 cubed. Okay. Can you combine them? Yes. You will get, let's simplify a little bit. So 16 minus 4/3. Yeah, 4/3. So it's going to be 44/3 times 2 pi. Yeah, looks like. Yeah, 44. So it's going to be 88 pi divided by 3. Yeah. Now, can you set up another integral? Essentially is the same. Okay, depends on which one you want to use first. So this is a domain. Okay, this is a region. So this time I'm going to so z is from 0 to 4. So from 0 to 4, I put it all side first. dz. So I begin with a single integral. Okay, take an arbitrary point z. This time I have to fill the solid using the disk. Okay. So the boundary of the disk is determined by x squared plus y squared equals z. Okay, right? Because it's a z, right? So the domain depends on z, and x squared plus y squared less than or equal to z. Okay, in the in the xy plane. So this is going to be double integral. And the z here, dA. Okay. But z is independent of x and y, so I can take the z out. Okay. Right? So this is going to be the area of this disk. The area of this disk is pi r squared. R squared is going to be z. R squared is going to be z. Right? All right. Okay, let me see the function. Here's z. Okay, for each z. Yeah, you get, yeah, that's correct. So now you find that the antiderivative of the square. So that is going to be right. So it's going to be 4 cubed pi. Now we get different answers. Okay, there's some computation mistakes. Clearly, right? So look at the second one is much simpler. Let's double check. And this is an integral. Okay. First of all, the single integral is outside. Z is upper bound for z is 4, right? Lower bound for z is 0. That's clear. Then for each z, you get a cross section with solid, which is a circle, it's a disk. Okay. So this disk, the area of this disk is going to be pi r squared. R is a square root of z, so r squared is still z. Okay, it's pi r, pi z. Okay. So you will get z squared pi. Then antiderivative z squared is going to be z cubed divided by 3. Okay. So you get 3. Now there was a small difference here. We have to double check the computation mistakes. Okay. Otherwise, yeah, let's see. My computation should be correct. No, the setting up is correct. Okay. So here's a d. Right. D has radius 2. Okay. Right. Because the largest circle on the top is x squared plus y squared equals z equals 4. Okay. Then for each point x and y in the domain D, you can draw the vertical line. So these are from x squared plus y squared to 4. Okay. Yeah, I think there was a computation mistake here. So z squared, when I plug x squared plus y squared, I have to square it. That's a problem. Okay, so that's where it's from. Where's the mistakes here? So this will be 4 squared. Okay, when I multiply this up, this will be fifths. Okay, and then that will be 6. Right, and 12. Then the rest of them is correct. Okay. So it will be 12. It's easy to make mistakes, right? Yeah. So 2 to the 6 is 12. After simplified, I guarantee that would be I think it's 64. I'm pretty sure. Okay, let's do the computation. After I simplified 12, 2 to the 6. Here's a 2 to the 2 square times 3. So after cancel out, it's going to be 4. Okay, so 4 times 4 is 16. Okay, 16 minus 16 over 3 is going to be 16. 2 over 3, right? And multiply by 2 is times 4. So that's why the result is 64 over 64 over 3. Okay, so different way to solve the problem. You should end up with the same answer. Now, if the answer is different, then one of them that was a computation mistake. It's easy to make mistakes like here, you know, because here x squared plus y squared is a square. So when I plug, so it's z squared. So when I replace z by x squared plus y squared, I should get x squared plus y squared and then squared. All right, so let's do the number 9. All right, number 9, it's a similar triple integral y squared z squared dv, okay? And this time E lies above the cone z squared equals x squared plus y squared, and below the sphere. All right, so this is a triple integral. Okay, so looks like we have to use the spherical coordinates. So we have to draw the graph first. Okay, it's this graph. This one has has radius 1. Okay, so so that is the region we're talking about. So if you draw okay, this is take an arbitrary point inside this region. Okay, x, y, z. This angle is a phi. If you project it to the xy plane, this angle is theta. Okay. Now clearly, theta is going to be between 0 and pi over 4. Okay. Now phi, theta is between 0 and 2 pi, and the rho is between 0 and 1. Okay. If we use the spherical coordinates, okay, it's rho and sine phi cosine theta, y equals rho sine phi sine theta, and z equals rho cosine phi. Okay, so this is actually this maps this rectangular box onto this region. Okay, described in the problem. Okay. So the actually it's going to be a box. Yeah, this is rho, this is a phi, that's called theta. Okay, so actually it's going to be a box. Yeah, this is a whole box. We send it to. Okay, but that to me is much better. It's a rectangular box, right? So okay, this triple integral, and here y is the square dv can become the triple integral of e bar, and y times rho is going to be z square sine phi, cosine phi, sine theta square, and then I have a row, right? I have a row square sine phi, okay, and a dv. So this is a yeah. This is coming from the Jacobi of this triple integral spherical coordinate. Okay. So what is next step? Next step is to evaluate this triple integral using iterative integral, because right now the box, the region is nice, it's a box. So you can express in the form like from 0 to 1, right? That's with respect to, right? From 0 to, let's say, pi over 4, from 0 to 2 pi, okay? And here's a row, square to the power 6, and sine square, then sine cube phi, cosine square phi, and the sine square theta, and d phi, d theta, and d rho. Okay, so you got those integrals. So now, how to evaluate? That can be separate. Okay, that's the first one. The second one, and the last one. Okay. And I think each of them the only thing I have to talk about, only integral I should talk about this one. And here, this one, because sine is going to be 1 minus cosine 2 theta divided by 2. So you have to change it to that one. So integral of sine square theta from 0 to 2 pi is going to be, I think it's going to be pi. Yeah, let's do one by one. This is going to be 1/7. Clear, right? Another easy one is 1 minus cosine 2 theta divided by 2. Okay. So the second one is 0. So integral cosine 2 theta over from 0 to 2 pi 0. Okay, it's going to be 2 pi, so it's just pi. So now we are going to work on the next one. I have to use a substitution. Okay, I let u to be sine phi. So du equals cosine phi. Du equals negative sine phi d phi. Okay. That's it. So when phi is going to be 0, it's a 1. When phi equals pi over 4, then the square root 2 pi over 2. And then I have a sine cube, it would be sine square phi and sine phi. Okay? So sine square cube is 1 minus u square, sine square phi. Okay? Cosine square phi is u square. And then sine theta d theta is a negative du. Okay? So you will get square root 2 over 2 to 1. And u square minus u to the fourth power du. Okay, so the antiderivative then you simplify. All right, cube. So I will take. How do I simplify this? I take a u cube out. Yeah, right. So then you combine them, you get as a simplified expression. So let's leave this answer like this. Okay. Then you get put back to that's a product of the three numbers being with a double integral. As you see that it's quite complicated. Okay. So number 10. Using the given, you are given this transformation. Okay. And given that, okay, evaluate this double integral 4x plus 8y dA, okay, where D is the parallelogram with vertices -1, 3, 1, -3, 3, -1, and the 1 and the 5. Okay. So here's the problem. So we are in the x to y plane. -1 and 5 is here. -1 and 3 is here. 1 and the -3 is here. 3 and the -1 is here. And 1 and 5 is here. So this is a parallelogram. Okay. So this linear transformation sends a rectangular domain in the UV plane onto this parallelogram. Okay, but we have to figure out what is the box here. Okay. You can solve it, right? Now let's solve for U and the V first. So let's backward. So this is a map, x equals quart of U plus V. Y equals V minus V divided by 4, right? But you can also send this back, right? By solving U and the V. So when we solve for U and the V, okay, let's do that. 4x equals U plus V, and the 4y equals V minus U. Let's solve for U and V. Okay. I do the subtraction. I get 4x minus 4y equals 4u. So u is going to be x minus y. Okay. So how can I get the v? The v is going to be 4x minus u. Right? Yeah. First of all, you do subtraction. Equation 1 minus equation 2. 4x minus 4y equals 4u. So u equals x minus y. Then after you get the u, then you can solve for v. So you get 3x plus 1. Okay. So actually, yeah. What happens here is the points along this line, okay, I'm pretty sure it has negative slope. Along this line, the v value is the same value, okay? So along this line, because when x, yeah, you can try this, right? And here's a 1, -3. This will be -1 and 3, okay? So when x equals -1 and y equals 3, so it's going v is going to be 0. Okay, v is 0. So this is horizontal. Yeah, let me find the pen. So this red line becomes here. So V0. Okay. And the same here. Let's try this. Okay. This line, when this is a point 3, -1, here's 1 and 5. So when x equals 1, y equals 5, so it's be 8. Okay, so v is going to be 8. Okay. Yeah, how about u, right? Then you look at this line. Okay, if you look at this line, you plug into this equation. Okay, -1 and 3, so it's -4. This line actually is -4. Okay, and for this line, when x equals 1, y equals -3, then you get a +4. Okay. So this line is going to be this piece. Okay. This line would be this piece. Right. So now you get a picture, pretty clear picture. Anyway, so you rotate a little bit and shift a little bit, right? So you map that. Okay. And what I have to do is to find the Jacobi, because this map, okay, this is going to be, let's call it the D bar. Okay, that's a D. Okay, double integral, right? Yeah. So according to the formula, 4x plus 8y dA is going to be the double integral D bar, 4x plus 8y, and then here the absolute value of the determinant, and dA bar. Okay. So I needed to calculate, this. This is going to be determinant. So derivative of x with respect to u is 1/4. The y value was it's going to be -3/4. Then the derivative of x with respect to v is 1/4, and this is going to be 1/4. Right, so dy dv. Okay, so the determinant is going to be 1/16 plus 3/16. So it's 4/16, it's going to be 1/4. Constant, 1. Right? Then 8x plus 4x plus 8y is going to be u plus v plus twice of v minus 3. Okay? Because 8y. Okay? So you're going to get 3v, u minus 6u, it's -5u. Okay? So now this double integral, it's going to be this double integral and 3v minus 5u and the quart and dA. Okay. Go back to the domain. So our rectangular domain, right? It's going to be from 0. V is from 0 to 8. U is from -4 to 4. So it's going to be integral -4 to 4. And the v is from 0 to 8. 3v minus 5u divided by 4. And that's the dv and the dA. All right, so let's evaluate. Entire derivative of this function is going to be 3 over 4. V is half of v squared minus 5 over 4 u and v. Okay, evaluate at 2 endpoints. So you just need to plug 8. That's going to be 4 times 2, 3, and 8 squared minus 5 u and 8. Okay, so let's simplify it. 24. And this 8 over 2 times u is 2u. So entire derivative will be this one. Okay. It is just going to be 24 times 8. $190, right? 192. So that's it.